Good afternoon, everybody. Thanks for joining us today. We're excited to continue the Thrust B series with a presentation from Dr. Tom Meixner at the University of Arizona. I think we'll probably have a couple more people tuning in, but we're going to go ahead and get this started so we stay on time today. So Thrust B focuses on innovative technological solutions using the data, models, and enhanced process understanding developed in Thrust A. These solutions include building to community scale resource recovery and reuse systems, hybrid, centralized, decentralized water infrastructure systems, fit for purpose water systems, green infrastructure, sustainable urban drainage networks, and resilient floodplains. The complete Thrust B series schedule is also available on our UN website, and I just today was able to add in a calendar to our website that will have display all the webinar information as well. We'll continue to record each webinar and post them to our YouTube channel. As always, I'll send out a link to the video once it's available. So please be sure to join us next week for a presentation from Dr. Jim Smith at Princeton University as he discusses flood hydrology and rainfall frequency. Okay, and with that, I'm going to turn the controls over to Dr. Meixner and give a brief introduction while he gets set up. So bear with us for just a second. Professor Meixner grew up in Rockville, Maryland. He received a BS in Soil and Water Conservation and a BA in the History of Science from the University of Maryland College Park in 1992. He subsequently received a PhD in hydrology from the University of Arizona in 1999. He was a professor in environmental sciences at the University of California, Riverside from 1999 to 2004. And since then, he has been an associate professor at the University of Arizona in the Department of Hydrology and Atmospheric Sciences, where he also serves as the associate head of the department.
Thanks, Sarah. I'm here with Yoga Karankandar, and then I'll just note that Tim Stevens is in the room, but Yoga is going to take over for part of the presentation. So I'm going to sort of give some background on sort of the green infrastructure, stormwater work we're doing here in Tucson, the modeling work that Yoga is doing, and then some of our connections to the other thrust areas that we've been working on. But first, I want to show you a video that Yoga found that our local newspaper, the Arizona Daily Star, put together about last year's monsoon season to just give you an idea of the sort of stormwater issues and phenomena that we deal with here in Tucson. So this is actually probably not in one of our study watersheds, but close by. It's the Feldman's neighborhood. You can see sort of wall-to-wall flooding, curb to curb, and even up into people's yards. This is actually one of our main streets in Tucson, Speedway, and that's a park. Actually, sorry, this is Stone, and that's a park that at the intersection of Stone and Speedway, two major streets. Here's a condo development, sort of water flowing out, and again, sort of this curb to curb and even beyond sort of street flooding. So we have this sort of nuisance to hazardous flooding. Last year, I think there were about 25 swiftwater rescues inside the city limits, not in drainage ways, but in city streets. So you can see sort of the problems that might entail with that. So green infrastructure is one of the things people are looking at to sort of help deal with some of this nuisance flooding among sort of larger scale Army Corps and Pima County Flood Control District projects as well. Okay. So with that, I'm also going to give you some context of the water supply available, because the other major factor in sort of people's interest in green infrastructure in Tucson is to see if we can use it to support vegetation and maybe sort of take the next step in ratcheting down per capita water use in the city. And then I'll talk about the changing urban hydrograph, the sort of biogeochemistry work we're doing, the modeling work that Yoga's been doing, and I'll sort of touch on sort of some of the work we're doing in connection to Daryl Jeanette's group and the impact of green infrastructure on urban canopy, and then the integrated impacts that we're looking at on the observational side that are sort of just getting off the ground, that'll feed into the modeling work that Yoga and Tim and Jim Smith's, Brian Bledsoe's groups are doing, and talk a little bit about a connection out to social science. So one of the things that we deal with here in the Southwest is the over-allocation of the Colorado River. So on this figure, it's just a figure from the Bureau of Reclamation showing water use within the basin and the water supply, a 10-year running average in the basin. And you can see sometime in the early 2000s, water use was greater than water supply. And that's a problem, because if you remain that way for a long time, you end up with empty reservoirs and all sorts of issues. And reclamation has projected that to continue. I'm skeptical that the water demand will actually go up, in part because nationwide, this is now the USGS estimated water use in the United States. You can see the total water withdrawals in the United States plateaued starting in about the 1970s and actually declined significantly from the 2005 to 2010 USGS water demand reports. As some of you might be familiar with, right, the report for 2015 will come out in 2019 because we don't have a unified database of water use in the United States. So the USGS sort of spends 4 years trying to pull that data together. I'm sure Sybil Charvel, who's on the line, can tell you a lot more about that than I can. But the point is that this sort of overall water demand in the U.S. has actually plateaued. And just for a finer grain sort of image, this is actually this is deliveries for single-family homes in Tucson since the 1980s. And back in the late 80s, early 90s, Tucson was about 171 or 170 gallons per person per capita per day. And by the early 2010s, we were down to 116 gallons per capita per day. And from what I've heard from Tucson Water, this trend has continued. The sort of water use per capita continues to decline. And so one of the things that we can contemplate, that I've contemplated in green infrastructure is part of this story in terms of, by better utilizing rainwater and stormwater, these per capita demand numbers can sort of continue to decline. There's a complicated story behind these declines in Tucson. Some of it's price, some of its availability, some of its cultural shifts and changes. But the sort of trend is sort of undeniable at this point. But the question is how far can this go, and what practices might permit it to continue might allow it to continue. Okay. The other purpose behind our work is, of course, sort of the widely documented urban stream syndrome. Right? We have increases in flow, resulting changes in morphology, some of which are imposed by the stormwater, but some of which we impose through cementation and formalizing of drainage networks to sort of make flow move more quickly through our cities. There are water quality impacts, which then have an impact on ecology. And these are driven by the changes in imperviousness, and particularly, I think, in our setting, the formal drainage network that street networks provide to sort of move water quickly from the uplands down into stream channels and on out of the system. And then people are looking at remedies, things like rain tanks and green roofs, permeable pavement, and largely the mode we'll talk about today in terms of the green infrastructure biogeochemistry work, sort of these unlined biofilter or bioswale systems that have become a dominant mechanism here in Tucson. Now, in Tucson in particular, we have data from Evan Canfield at Flood Control and Eric Gallo, who's a research scientist in our group, showing that as you go from undeveloped systems to urban systems, you get a significant increase in runoff ratio. So you can look at that top graph and think of it as runoff ratio, or fraction of rainfall that would be harvestable, is the way Evan Canfield has put it. And those differences in sort of how much rain is available for use, if you will, are greatest at the smallest size. When you get up to large drainage ways, you know, even 1 square kilometer, but certainly up to 1,000 and 10,000 square kilometers, the urban and undeveloped systems seem to converge in their flow. Now, not only do we have more runoff in our urban system, but it also occurs more frequently. On the lower left, you're looking at a figure that shows undeveloped and urban watersheds for how often runoff is generated when there's a rainfall event. So that's not 60–70% of the year for the urban settings, but what that is when it rains, do we get runoff? And in undeveloped systems around here, it's about 20%. So our native rangelands, you know, 80% of the rainfall events just absorb into the ground. Whereas in the urban area, it's more like 70% of those rain events result in runoff generation. So there's more runoff, it's happening more frequently, and on the lower right, you can see that it occurs for a longer duration of time. So while we tend to think of urban systems as flashier than the natural systems, we start here in the Southwest with a very flashy system in the first place. and urbanization sort of, if you will, exacerbates and extends that, but now we also get runoff for a longer duration because there's not the ability for that water to re-infiltrate as it does in our natural rangelands because of the formal drainage network that our street networks provide, among other factors. Okay, so we're going to first sort of focus on the biogeochemistry of these bioswale systems and how they might be influencing more the biogeochemical side of things. And for that, I think we need to have sort of a concept on the upper right here of sort of what these bioswale systems look like. They're largely terminal or flow-through systems pulling water off of streets. And those then represent sort of activated biogeochemical reactors. So if you look at the lower on the figure on the left, we don't really have permanent biogeochemical processing here because we run out of water. But we do have activated systems like these bioswales that are reactant restricted in that we essentially, you must add water. And these bioswale systems add the water when it does rain. And so these GI systems are looked at for these, maybe this biogeochemical function, some vegetation function, but also the hydrologic services that we're looking at them for increased infiltration and potentially reduced peak flows, flow volume, and perhaps reduced flashiness in these systems. Okay. Sort of taking this together, if you will, a trajectory we might be on is in our undeveloped watersheds we have smaller runoff volumes, lower peaks for a shorter duration of time. We go to developed, we go to this blue line. We get higher peaks that occur sooner, but then for a longer period of time and a larger overall volume. And with GI, we might be trying to move these systems back to this more undeveloped state, but unlikely, sort of given the geography of the system, that we're going to get back completely to an undeveloped state. Evan Canfield at Flood has said, well, maybe we could capture the first inch of rainfall. And when you say, oh, that sounds like quite a bit of rainfall, basically just 2 weeks ago tomorrow, there was a part of town that got 2.5 inches of rain in 30 minutes. And there's really not much of a way to sort of design a GI system that would capture a full rainfall event like that. So, okay, so with that, we'll sort of move into sort of some of the motivation for the biogeochemistry work we've done. In biogeochemistry, there's sort of a framework out there of hotspots and hot moments, and these GI systems represent an intentionally built hotspot to try to encourage both hydrologic infiltration, but it also encourages vegetation growth and biogeochemical reactions. But in our system, those are also going to happen as hot moments. They're going to be small, brief periods of time in which much of that happens. And in dryland systems, we know that precipitation is episodic. Microorganisms tend to become inactive during dry periods. These systems essentially, if you will, almost completely senesce and go completely inactive during the long dry periods. Typically in Tucson, it's not atypical to have a year like this where for 3 or 4 months there's basically no measurable rainfall, or if there is, it's on the order of hundredths of an inch, and so it doesn't become biologically relevant in any significant way. During that dry period, nutrients and substrates for biogeochemical processing accumulate, and they're then available for when it does rain, for those nutrients and water to either be transported to GI or those nutrients that are available in the GI to be activated by the water that becomes available. So you sort of start with this idea that green infrastructure could be a hotspot for biogeochemical cycling, and then we need to look at, so what does that mean? How does that play out? Okay. And so for this study, my master's student Tyler Rockhill found 20 sites, 10 in the Bronx Watershed, 10 in the high school watershed, and 5 GI soils were 5 samples per basin were collected within the GI, 5 control samples. Samples were homogenized. This is sort of really a way to sort of get around. We can't analyze 5 soils for 20 basins and 20 control sites. You get into difficult sort of manpower and sort of management of the samples. So the homogenization allows us to sort of, if you will, statistically average those soils together before we do the analysis. Samples were homogenized, dried, sieved to 2 millimeters, and then separated into subsamples that we then did further analysis on. Okay. Just to give you an idea of sort of the placement of these, one of the things we did was we sampled basins that were of 5 basins that were flow-through basins, so where water is essentially designed to flow through these systems, versus terminal systems. And so one of the comparisons here is these sort of basins that receive water and it simply infiltrates, and they serve more as a lentic or lake-like environment for reaction, versus flow-through systems that might behave more like a stream or a lotic system, as one of our experiments. And you'll see later on that has some impact on the biogeochemical function of these systems. And then here's the same figure for the high school wash, just to give you an idea of sort of where these places are. In the center, on the upper left of the figure here, you have the University of Arizona campus. Yoga, Tim, and I are currently sitting right about here. So what do our results look like? On the left this is a figure you saw last week at the UN meeting, but on the left is sort of Jack Anderson's sort of photo montage of what these flow-through and terminal systems look like in the Bronx, the BX, and the high school HS system. So on the left is flow-through, on the right is terminal. Bronx is the first column in each of those sort of twin panels. High school is the second vertical panel. And you can see that the surfaces of these systems look quite different between the watersheds. Of note, the Bronx systems were largely installed within the last 2 to 3 years. The high school wash systems were installed about 10 to 15 years ago now. So they've had a significant period of time in which they've at least semi-equilibrated with their environment. Now, one of the things we saw in these systems on the upper right is an increased water holding capacity in the GI soils. This is certainly in part by design. People intentionally add amendments when they're building the GI, typically organic amendments, but also some coarser sands to try to increase the water holding capacity. But we see that in both flow-through and terminal systems, versus the control soils have much lower water holding capacities on the order of 30% versus about the 50 to 60% we're seeing in the GI soils. On the lower panel, you see sort of just in the textural triangle, the black and white dots, essentially the black, the GI, the white, the non-GI. So there isn't a significant difference in the textures of these soils. So it's not mineral amendments that these people are making that seem to be maintaining these differences. It instead turns out to be, we think, soil organic matter percentages. So here we're looking at some of the soil chemical properties differences. And again, soil organic matter is significantly higher in both the flow-through and terminal systems versus the control soils. And that carries over into total carbon and total nitrogen. It doesn't turn out to be a difference in the carbon to nitrogen ratio. So there's not a difference in, carbon to nitrogen ratio is often used by biogeochemists to sort of look at, well, how labile is the organic matter? The lower that ratio is, the less carbon there is per nitrogen, if you will. And that makes it's generally thought of as making that organic matter more reactive. And we don't see that. So it's simply an abundance difference, not a quality difference in that organic matter, with the GI basins having just significantly more organic matter. The control soils have about 1 to 2%. The flow-through and terminal systems having maybe 6 to 10% organic matter, probably because of the higher just biological productivity and vegetation growth of these systems. Okay, so what did we see in terms of this biogeochemical response? So here, there's several different variables that Tyler was looking at in this experiment. And this first one is control versus GI, which you see on both the left and the right are a GI to control comparison. And then small events, essentially a rain event that might just be rain falling on the soil, wetting it up, versus a large event that might be more like a flood event that comes in. And what we see is large events have greater respiration response, which is the response variable on the y-axis. Not surprising, but we also see that the GI systems have significantly greater biogeochemical response than the control systems. And so, the GI is serving as a greater reservoir of organic matter and a greater respiration response. So these are, if you will, hot spots. They're hot locations on the landscape, but they're also more responsive when there is water available. They have a much greater response than the control sites. Okay. Like I said, one of the things he was looking at was flow-through versus terminal. And then, again, this is that same cumulative CO2 response. And we again do see a statistical difference between the flow-through and terminal sites, with the terminal locations, these more terminal basin where water comes in, but also organic materials and other materials come in and get deposited and perhaps accumulate. So we do see a greater respiration response there. We didn't see a difference in soil organic matter. That may simply be a matter that for the soil organic matter value, we didn't have a large enough statistical size. But we do see a difference in behavioral response when these wetting events happen, that terminal or basin systems are having a greater response, particularly to the large event, than the flow-through systems are. So more of a typical bioswale system that you might see. Okay. So the lessons from this biogeochemistry: GI basins have different physical and chemical properties than their control soils. The magnitude of this Birch effect, this sort of episodic response biogeochemically of dried out soils to increases in water. There is an effect on sort of the physical properties, the water holding capacity, the soil organic matter. There doesn't seem to be a difference in canopy cover or vegetation soil texture, some of which I touched on, some of which I didn't in the slides. But then the magnitude of that respiration response is greater in the basins, whether terminal or flow through, because of the soil organic matter and the total carbon. So we do see the GI is functioning as people imagine it would, as more of a biogeochemical reactor, with differences between the flow through and terminal systems. Okay. So with that, I'm going to hand over to Yoga to sort of have him talk about some of the work he's been doing on modeling the hydrology of these systems and building the Kinneros models, and some of the tools we need to build Kinneros models of these urban watersheds. So go ahead, Yoga.
Thanks, Tom. I hope everyone can hear me all right. So first up, when it comes down to modeling urban areas, there's a couple of challenges that we have to face. If you look at the figure on the right, our high school wash is a big watershed. There's around 1,400 residential lots on that one. So to model something at that level of detail can be challenging. Next is, how do we represent flow-off, flow-on processes on each of these lots if we look at that fine level of detail? And then bigger watersheds like this will have subsurface stormwater conveyance on major streets, and in this case we also have a natural channel running through the watershed. And then once we start putting in green infrastructure practices, how do we model that? So that's some of the questions that we have to face when we try to model an urban setting. And then when we try to actually do that, do we have tools to assess all these things? Do we have tools to assess the layouts of the houses, commercial areas, or even open areas? How do we assess stormwater management systems like your drains and CSOs maybe for flood mitigation? And then if we start putting in green infrastructure practices, is there a way to quantify water supply that we might be able to augment through those practices? And then finally, a big concern out in the east is water quality. That's a part of the whole urban setting. Sorry about that.
That's okay.
All right, so keeping all that in mind, we decided to come up with a tool that can help model urban areas using the Kinneros model. Kinneros stands for Kinematic Erosion and Runoff Model. And what we did was we tried to use this model as part of a GIS framework, so we can use readily available spatial data and visualize spatially model parameters and results. What the Argo Urban tool helps you do is it gives you a step-by-step process into setting up your input data, setting up GI practices, then running the model, and then visualizing the results. You start at a lot scale or a subdivision scale, and then you can put in 3 kinds of green infrastructure practices right now: retention basins, permeable pavements, and water harvesting systems. And I'll talk a little bit more in detail each of these sections in the forthcoming slides. So the Kinneros model was designed to work with smaller watersheds ranging from 100 to 200 square kilometers. And what it does, it represents hill slopes as rectangular sections, basically, with 2 rectangular sections draining into 1 channel and overhead rectangular hill slope as well. what we did was we modified one of these rectangular elements to represent an urban element. And what that can do is go to a fine detail to represent each individual lot. The good things about Kinematic is it's spatially distributed model, and it routes water physically and dynamically using differential equations. And for infiltration, it uses a modified Smith-Paul-Lange equation, which is similar to a Green and Abt equation. So as Tom showed you this figure already, we're looking at two watersheds to begin with. My work over the past few months has been focused on Bronx simply because it's a smaller watershed. It's a little less complicated as compared to high school wash because it doesn't have a natural channel in it, and it's just easier to model in a way. And then here's a zoomed in version of the Bronx watershed. The pictures alongside are from July 19th, 2017, when we had an inch of a rain event in 1 hour. And you can see that most of the water is flowing off the streets, and then there's this concrete channel running straight through the middle where the water is conveyed out through underground culverts as well. So this is what we're trying to model in our situation. The red box just shows in a zoomed in area where I'll show you some more pictures and maps for that particular area as I talk about the modeling process. So biggest challenge was how to understand how the water is going to flow through our watershed. You can go out and walk and see how the water flows during a storm, but we needed a quick and easy way to do that. And with high resolution LiDAR data available, we thought that was the way to go. So LiDAR comes in points, which is the top left figure, which can be converted into a digital elevation model. We used 0.5 meter resolution. From that, we can create a flow direction grid, which just shows you how the water is going to flow at that 0.5 meter resolution. And then that is all accumulated into showing us how the water is going to accumulate on a cell-by-cell basis going downstream. With that, you come up with a map which looks like this. So for a Bronx watershed, the blue lines indicate how the water is going to flow off the streets into that concrete channel in the middle. The only limitation on this is because it's a digital elevation model, we can't assume underground flow on this. So this is all overland flow. So that's something we have to keep in mind when we're modeling this. With this map, what we can do is start representing that in our model. So on the left-hand side, the green lines are the same lines that you saw in the previous slide, and the blue lines are what we draw on a map when we're actually telling the model how the water is going to flow. And the model assumes the figure on the right from that diagram. So all the water is going to flow from the lot onto the street and then follow the path along the street. The next step is to give in some input parameters to the model. For our lots and streets, we need dimensions. So how big is the roof? How big is the driveway? What's the width of the street, the slopes, etc. For land cover parameters, we need the roughness of the soil or the surface, the interception as far as how many trees are around, and how much canopy cover will affect the interception value from the rainfall. And then we also need soil parameters to determine infiltration and then subsequent runoff. And those are all the bunch of parameters that we need. For our quick and easy way of modeling this setting, we use the Surgo data, which is pretty high resolution and it's nationally available. But we do understand that there's limitations with using that data because in an urban setting, we do have soil compaction and that changes our infiltration parameters significantly. So that's something to keep in mind. If you have field data for soils, we highly recommend using that. But if you're running out of time, you don't have time to go out and take field measurements, then this is a good backup to use. What drives the model is precipitation, and Kinematic 2 requires time intensity pairs or time depth pairs. The Agua Urban tool is designed to accept databases from the NOAA website, or you can also specify a hydrograph or just specify a depth with the duration and the number of time steps you want to divide that storm into. This is the July 19th storm I was talking about, 1 hour, 30.5 millimeters, and we divide into 12 time steps to get a hydrograph which looks like this. And as far as connecting other projects in the trust, Jim Smith's group is working with the rainfall frequency data, which we'll talk about in the next webinar, and we plan on using that data for our watersheds to run the models. The way Kinematic represents everything in that rectangular element is what you see on the left side. If you have your yards, they go into a section called the directly connected pervious section or the connecting pervious section. Your roofs are represented by the indirectly connected impervious section. If your driveways are represented by the directly connected impervious sections, and you can also add retention basins in the middle. And then if you have swimming pools, they can go into the non-contributing areas, which are basically your sinks so that water doesn't flow off those areas. On the left to the top, you can see a typical lot and how it's converted into a rectangular element. And then what Agua does is it creates all these text files that Kinematic needs to run. So that one lot gets represented in text format as seen below on the left. We use all this to run our models, and then Kinematic again prints out text files as results, which Agua imports and then can spatially visualize them for you. So what you're looking at right now are runoff volumes from the lots and the streets. The green is the volume coming out of each individual lot. The darker the shade of green, higher is the runoff. And the blue is accumulated runoff of the streets as water flows down the watershed. Again, the same concept, darker the blue, higher the runoff. And to give you a comparison of how that the blue is becoming darker going towards the left, you can look at the flow route that we assumed to get that result, which is the smaller diagram to your left. So that's one of the outputs that you can see. The next output is infiltration. This is again infiltration volumes on each individual lot, and then darker the color, higher the infiltration. And then we look at hydrographs at various points throughout the watershed or at the outlet. This one specifically at the outlet with the rainfall hydrograph in it as well. So you can visualize these results. Now, if you're thinking, what can you do with all these results? If you look at runoff, you can start looking at areas where there's greater runoff as compared to its neighboring lots, and then maybe decide on putting in some infiltration practices over there. Or maybe the lot can make use of harvesting all the water that's coming off the roof for landscaping purposes or something like that. And then if you look at accumulated runoff, you can start thinking about bigger stormwater management practices, like a bigger retention pond, or maybe even considering subsurface stormwater conveyance in those situations if there's a value at risk at one of the overland sections. Then going forward, from the peak flow results that we get, what we can do is you can start putting them in other models. This is what Tim did during his time here in Tucson. Do you want to talk about it, Tim?
Sure. So this is the storm from July 19th that Yoga previously mentioned. And the hydrograph that you see in the top right is the output from one of the Kinematic 2 runs. And we were able to take the peak flow from that hydrograph and route it through a one-dimensional steady flow HECRAS model that we'll talk about probably in a few weeks. And on the left is the on the top left are the results from that HECRAS simulation. And if you see the intersection to the left of that figure where the cursor is at the moment, that's where the picture on the bottom right is. And based on visual inspection from being out there, it looks like the combination of the Kinematic 2 and the HECRAS model do a pretty adequate job of modeling that flood. We have some further refining to do on that, but first inspection is pretty good. And then the bottom left is just the uncertainty in the 100-year design flood from USGS regression equations and the standard error of prediction around those.
Yeah. And I've just, as an observation of this, you can see here to the left of that intersection that we have pictured, you can see that the the 100-year design storm and the smaller one fit completely within the channel that's been designed. But if there's two standard deviations off in Tim's calculations, you start getting widespread street flooding and probably damage with that. So, okay, thanks Tim, and thanks Yoga.
Oh yeah, and from this, what we're doing right now is we're going to wait for some summer storms to hit Tucson so we can calibrate and validate our model for the Bronx Watershed. Once we have that done, we'll move on to high school as well and start collecting input parameters for that and do the same process for that. And then we'll start putting in GI practices on our watersheds to see if there's a spatial effect on flood mitigation and water supply, or how many practices help us get to a particular level of peak flow values throughout the watersheds. Like Tim talked about it right now, our results can drive HECRAS models for floodplain analysis, and then we might also consider using SWIM for subsurface water analysis. And then once we're done with that, we'll start looking at a single lot to on a more continuous basis to assess evapotranspiration, soil biogeochemistry, and plant growth in terms of its flow off and flow through processes. And then we'll run similar analysis on maybe some other watersheds in Tucson as well.
Sorry. Okay, so I just wanted to talk a little bit about, like I said, some of the connections we have out to other projects, and then how we're going to scale this up to larger scales, at least here in Tucson and elsewhere. So, you know, we have this interest in GI related to urban forestry, and that's more closely related to Daryl Jenret's project within Thrust A. But Charlie Papuga's lab has been working on essentially the concept that GI, what she's seen in past eco-hydrology work in arid systems, is that right when you get small events, you get the surface soil wets up, but the plants don't really respond. They don't green up. All that water that comes in basically evaporates. And so you have sort of case 1 and 2 here on the right. You quickly go from a little bit of wetness on the surface soil to dry soil again and no plant response. With large rain events, you fully wet up the soil column. The surface soil dries out, but a few days after rain, you now have green vegetation that can evapotranspire. And the conceit here is that GI pushes you more to case 3 and 4 more often than without GI in our setting, and thus you get added vegetation growth. And to sort of assess that, Anthony Lukacic has been monitoring 2 sites, one here on campus that has both GI but then also has active irrigation, and a watershed management group, a local NGO that's involved in rainwater harvesting and GI practices in the region, which is primarily passive. In fact, you know, they haven't irrigated yet this year and in the last 2 years at the site. And so he's monitoring things like soil moisture and tree sap flow to look at sort of really the plant physiology response and then the micrometeorological response to the vegetation is having. In parallel to that, Kayla Pope, our undergraduate researcher this summer, looked at vegetation growth in both the Bronx and high school watersheds. Her Bronx watershed results weren't statistically significant, which isn't surprising. As I mentioned earlier, that GI has only been in place for 2 to 3 years. But the comparison she ran on the high school wash showed that there was an increase in canopy growth over the period from 2005 to 2015, and that the average change in height and canopy in the GI was about almost 2 feet versus only a little bit under 1.5 feet for the regions without GI. And so we are seeing an effect of the GI on canopy growth, at least in the high school wash watershed, where we've had a decade-plus time for the GI to actually have an effect on the system. But sort of a caveat there is, you know, GI, you may install it, it may not have the initial effects that people want. It may take a significant period of time. Okay. And then another PhD student, Neha Gupta, has been working on sort of trying to understand how stormwater infrastructure varies spatially in Tucson. This will later feed back into Yoga and Tim's work, among others. On the bottom is a figure from Rebecca Hale, sort of showing Scottsdale, Arizona, going from a very rectilinear gridded pattern in the early part of the mid part of the 20th century to much more of a natural channel form here in the latter part of the 20th century in terms of the growth form, and the early part of the 21st century. And we see largely a similar pattern, right? The Flood Control Act of in the late 60s sort of changes flood development styles and flood management across the country, and the development form then in turn responds to that. And to look at this, we want to understand, well, what's the linearity response? We know that individual GI systems may serve as hydrologic reactors, biogeochemical reactors, but we really want to look at the impact of the density of the green stormwater infrastructure, get information about how these basins actually respond to runoff events. And our conceit is that as you implement GI, there's probably some small level which there's really no impact on the watershed scale effects that Yoga and Tim are modeling. But there is at some point you start having an effect, but also at some point you've implemented enough green infrastructure that you're no longer going to have an impact on watershed hydrology. And to look at some of those questions at a more observational level region-wide, we have a larger number of watersheds that we're studying. You know, we have the high school and Bronx watersheds that we've talked about. We have an Alamo Wash, Arcadia Wash watershed in sort of the middle part of town that has a similar growth form but a little GI. We have a nice control watershed that the picture on the upper right is from it, this Atterbury Wash that largely drains the crash zone for the Davis-Monthan Air Force Base. And so it was a nice undeveloped control essentially within city limits. And so we've installed pressure transducers to these, and that data will be available for people to model sort of these larger scale systems in our setting here. And then the final thing is sort of a connection out to the social science. Neha has been working with one of Adam Henry's grad students, Emily Bell, and looking at sort of where the social sciences and natural sciences interact. There's obviously things like runoff quality and quantity that are really purely natural science foci of the disciplines versus things like capacity and institutional barriers and competing interests, which are purely social science. But there are interactions at temporal scales, temporal changes that natural sciences study that have an impact out into the social sciences, spatial variation, and then the disturbance and crises that natural science can study in terms of floods, how they cascade into the social sciences. Okay. With that, we'll wrap up. So conclusions, you know, sort of the stock and trade, sort of arid, semi-arid, effective urbanization is sort of this increase in volume, frequency, duration, and peak of flow events. And with that, an opportunity, since there's more water more often for a longer period of time, an opportunity to help with water security issues, and maybe have some small, I think as Brian Bledsoe sort of pointed out to you and me last week, right, GI is not going to solve your flooding problems, but you know, it might help with taking off a little bit of the peak, which can make a difference in some extreme events at least. So GI does increase infiltration, biogeochemical response. The modeling is proceeding apace, particularly I think with Tim here this summer. Yoga and Tim have been able to sort of see how Kinross and HECRAS can sort of on the very detailed level, how do you technically connect them and connect the outputs from one as the inputs to the other, and had a fairly successful sort of simulation of that July 19th event. So the proof of concept that we need going forward. And then just finally, you know, we're trying to sort of connect our thrust area out and the work we're doing here out to these other thrust areas in both sort of the urban heat, vegetation work of Daryl Jeanette in Thrust A, and then the social sciences work that's ongoing. So with that, I will finish and ask if there are any questions.
Wonderful. Thank you, Tom, Tim, and Yoga. That was actually very informative for a novice like me. So I know what you're doing now. I'm waiting for the question queue to fill up. I don't see anything as of yet. Do you guys have any closing remarks or anything else you want to add?
I don't know if we have anything to add. I mean, I think we're very much looking forward to this meeting in Athens in about a month, where Brian's group with Tim and then Jim Smith and then at least Yoga and Phil and probably myself will come sort of figure out what we're doing. And I think we have Liz Mack coming, and I think Sharon Harlan coming down too to sort of connect on the, particularly on the floodplain side, you know, to connect that to some of the social justice and social issues work that's ongoing within UN. But
Great,
like I said, Tim being here has sort of helped us, I think, giving him a picture of what a very different environment than the ones he's familiar with in Colorado or Georgia and Tennessee is like, but then also this very important sort of technical back and forth between him and Yoga. So.
Wonderful. So we did have a couple questions pop up. The first one is, how is each different storm event modeled?
Take that to Yoga. So it's the Kinematic version he's running right now is not a continuous model. It's
an event-based model right now.
Yeah.
So you'll specify your storm event, like I said, in time depth pairs. So if it's an hour-long storm event, you just split up the volume over that hour, and then Kinematic will model it in the time steps that you specify. For our case, it was 12 time steps. So for each time step, it will run that volume for infiltration and then runoff, and goes down on that path. We are trying to work on a continuous version so we can do annual simulations and then also keep initial saturated conductivity into the soil, so infiltration parameters will change with water content in it. But that's in progress at the moment.
And you mentioned that briefly in terms of talking about using that continuous model on a lot scale, to sort of look at the strategies you might use. If you're going to capture water, say, in a tank, you need to know how that water might get used over time, because how full the tank is then affects your flood response. So some details like that will need to be built in. So
I hope that answers your question.
Yeah.
Yeah, we'll see if there's a follow-up.
So Sybil, sorry, Sarah, just a technical note. As a speaker, I can't see the questions that people are sending in by chat. I don't know if that can be changed for future.
Yeah, no, that's good to know. It all depends on how your dashboard is set up. So.
Yeah, and I understand that it could be a user-oriented problem. So.
Yeah. The next question is there a reason why you use Kinematic instead of swim?
Yeah, because in Tucson, most of our water is surface flow or overland flow. Swim is more, from my understanding, better at modeling all the subsurface drainages. Although swim is also point-based in a way, whereas Kinematic is more physical and distributed. So there were a couple of those reasons that we decided to go with Kinematic.
And so does swim capture infiltration losses?
I didn't think so.
Yeah, my understanding is swim doesn't capture infiltration losses, which is sort of the foundational aspect of Kinematic is the loss of water in conveyance in channels to infiltration losses, which is a key aspect of arid, semi-arid hydrology and ephemeral systems in particular. And that's, swim is very much designed as an urban infrastructure pipe flow and channel and line channel flow model is my understanding. Versus Kinematic being this, it comes out of being developed at Walnut Gulch to look at rainfall runoff events in sort of these arid, semi-arid rangelands with significant infiltration losses in channel systems. So.
How does Kinematic compare to the SWAT model?
SWAT is more larger scale, so those watersheds can be really big. It's also continuous. Kinematic is better at modeling smaller scales, around 100 to 200 square kilometers, and it's mostly an erosion-based model as well, whereas SWAT can also model water quality really well.
And Kinematic also, right, again, sort of the physical representation of the processes, one of the main simplifications Kinematic makes is this turning the watershed into a two-leaf book, or at the headwaters, this third leaf of the headwater area. Whereas SWAT really takes a curve number approach and propagates sort of the hydrology using that curve number, and if you will, SWAT is better at larger spatial scales and at coarser temporal resolution, whereas Kinematic is this more focused on event and short time scale processes and small spatial scale processes as a result.
Okay. The final question I see here is, does each green infrastructure that's modeled, are those based on the parameters from the biochemical studies?
Yeah, so we've been building up the data that Yoga will need in terms of, I didn't show it here, we do have infiltration measurements, we do have hydraulic conductivity measurements in these basins as well. We just haven't compiled them in a way that's the question that was being asked by the student is different than this. He was sort of looking at max infiltration rates over time as these basins age. But we do have data that could be imported into Kinross to sort of look at basin size and infiltration rates. So that's available. I don't think Yoga's gotten to that simulation step yet.
Yeah, just to add to that, we were still preparing the watersheds to model in their current conditions, mostly without the green infrastructure. Once we have that down, we'll start adding in the green infrastructures as well.
Wonderful. All right. Well, I haven't seen any new questions trickle in, so I think everyone's feeling pretty up to speed or just completely enamored and amazed, but both are good. So thanks everyone for joining. As always, I'll get this posted in the next couple of days here and send out that link so you can share it with anyone that may have missed today's presentation. Thanks for your time, guys, and we look forward to seeing and, well, I guess hearing from everybody next week for Jim Smith's presentation. Yeah. Have a good afternoon. Thanks for tuning in.